So the question was posed, what type of bond is involved in the sharing of electrons? I know I've asked you this before, but I just really want to make sure that we're all on the same page. See what we came up with. Sharing of electrons, covalent bonding, very good. Covalent, yeah. So now if I asked you another question, let's say I ask you what type of bond involves the giving or receiving of electrons, what would you tell me? I do expect you guys to be participating, taking notes and plugging answers into Pear Deck. See what we came up with. Ionic. Very good. Now if I asked you what type of bond involves unequal sharing of electrons, what would you call me? What would you call me? What would you tell me? Don't call me names. What would it be called if you unequally shared electrons? Unequally shared electrons. Tricky. Shh. Typing does not involve talking. Did you guys enjoy your break from me? 2 days off? You missed me. Yeah. See what you have. Polar, close. Polar covalent, perfect. There you go. Unstable in French. Oh. Polar, like the bear. Yep. Oh, hydrogen bonding happens between polar molecules, which we'll talk about that later. I don't know what that last liaison is. Unique. Today, yep, they should be up there. They should be up there right now, but don't do it now, please. Okay. I never put them the day of because then I have kids cheating, and so I always wait. Okay. Maybe yesterday afternoon, the results. Oh, maybe I didn't click the button. Well, it should be on there then. Okay. All right. So today we are looking at what is called polarity. Your Pear Deck code is up front. Question? Yes? Let's not worry about that. You can shut the machine off and turn it back on, but if Pear Deck doesn't work for some reason, I said just take notes. So go ahead and just take notes with us. It's not a perfect world. Sometimes things don't work. But you can always shut the computer off, turn it back on. That usually fixes most issues. But I'm not going to stop lecture to fix a computer right now. But don't worry. If it doesn't work, you can still take notes with us. So looking at polarity. In some covalent bonds, the shared electrons are attracted more strongly to one atom than to another. We're going to talk about water. We're going to do a lab over water. And as a result, one end of that molecule is going to have a partial negative charge, while the opposite end has a partial positive charge. Now, molecules with partial charges on opposite ends are said to be polar. So when you look at the word polar, and you think about magnets, or you think about, ends of the biosphere, what does the word polar, what's the root of that you guys are supposed to, you think, take out of it? What do you guys think? What is the root of that word polar that you're supposed to be taking out of it? I don't think you're...
I tried it on my phone, though, too, and it still wouldn't let me in.
Did you shut the computer down? Turn it back on?
No, not yet.
That's what I wanted you to do. No, turn it back on and try it again. Let's see what you guys came up with. I was just trying to fix the computer. Came in late. Deal with that stuff later. So poles, yes. Opposite poles, right? Positive and negative poles. How did you do that? I have to check that out. I don't know how you did that. 2 ends, poles, yep. And usually poles are oppositely charged, right? Or like north and south, like on a magnet, they're positive and negative. Batteries have poles, polarity, right? Positive and negative charge. Okay? And so when I say poles, I'm often referring to a charge. So the partially charged ends of a polar molecules attract opposite charges. Go figure. Opposites attract. We already know that from ionic bonding. Put that thing down. I'm going to need it in a minute. So because of this behavior, polar molecules can dissolve other polar molecules and ionic compounds. So if you look at water, we know it can dissolve sugar and salt. Nonpolar substances such as oil, grease, and wax do not dissolve well in water. I want to see what you guys learned last year. Okay? I want you to draw out chemically water dissolving salt. Let me change that real quick. I want to actually switch to a blank canvas. There we go. Okay. I want you to draw water dissolving salt. I'm going to draw it with you in a minute, but I want to see what you come up with. I want you to chemically draw it. Let me start you out with one of the molecules. Okay? There's the first one you'll need. It's also known as H2O. That will get you started. Please now, on your own, please show me water dissolving in salt. See what you guys are coming up with. Okay, we got water, good. It'll post it automatically. Keep going. See what you guys come up with. Show me water dissolving salt. Dissociating salt. It's a technical term. Doesn't really dissolve it. A little bit, yeah. You all right? He's not going to be tomorrow. It's coughed on it. All right, let's see what you came up with. See if anybody got the perfect answer. Not done yet? Okay, I'll wait. I'm getting some interesting ones as I walk around the room. Let's take a peek. Looking for a right answer. Whoa now. Close. So I actually want everybody to flip your notes over, or actually you can do this off to the side. Find an open spot. We need to get into this a little bit more. So you're kind of off to the right track and kind of off at the same time. So let's see what we're looking at here. I'm going to actually go up to the board and draw this, just because I want it to be a little neater. So if we look at oxygen on the periodic table, what number is oxygen? 8. What family is oxygen in? 6. So it wants to bond how many more times to be happy? 2. Okay? So that's where we get H2O, right? We know that. The thing I don't tell you is this. when we first talked about covalent bonds in water. If you look at hydrogen on the periodic table, please look at it. How many electrons does it have? 1. Oxygen has how many in its outer shell? 6. So, are they on different ends of the periodic table? Yeah. What type of bond would they normally form? I heard ionic. Because they should be oppositely charged, correct? Why do they not form an ionic bond? Because if hydrogen gave up an electron, it wouldn't have any, right? And then it basically wouldn't exist, and it wouldn't be able to interact with anything. So hydrogen cannot give up an electron. But because oxygen, how many protons does oxygen have? Don't say 6. It has 8. It has a lot, right? Because it has a lot, it has a lot of electrons, so it's said to be electronegative, more electronegative than hydrogen. So the electrons are going to get pulled away from hydrogen a little bit more than oxygen. Do you understand that concept? It's like if I'm bigger than you and we're sharing a meal, I'm going to get a little more of that meal, okay? Same idea here with oxygen and hydrogen. Because of that, hydrogen is slightly what? Positive. This is called polarity. This is a polar covalent bond. The electrons are still shared. Everybody with me there? But they're shared unequally. They're not given away. They're not taken. It's not ionic. These are not ions. Okay? But it is not shared equally. I always say, you know, you got oxygen over here, and oxygen is kind of like, you know, this electron hog, right? Right? That's how I remember it. You got this little piggy over here taking all the electrons in. So if I were to ask you to put, let's say, sodium, which is salt, right, and oh shoot, that's too bad of handwriting. I got to get rid of that. Let's do this. So if I asked you to dissociate NaCl, okay, and then I asked you to, what's the oxidation number of sodium? Please tell me. What's the oxidation number of sodium? +1. What's the oxidation number of chlorine? -1. That means they're held together by what type of bond? Ionic. And if I put them in a solution that is polar and has a charge, is it going to pull on the ions? The answer there is yes, sir. Yes. Okay? So if this happens, this sodium will actually be attracted to the negative end, the more electronegative end here, and chlorine is going to be attracted to the positive end here of water. And this is basically why water is able to separate or dissociate or dissolve salt. You get that? So will a polar compound easily dissolve an ionic substance? The answer is yes. Why? Because it is polar. If I put a nonpolar compound in water, something covalently bonded, will it dissolve as easily? No. Let me give you an example of that. Butter, oil, protein, an egg. Stick these things in water, do they dissolve? No, because they are covalently bonded biomolecules. All right? You understand that concept? Okay. So polar covalent easily dissolves other polar things, and it also dissolves ionic compounds easily. Let me give you one more example of a polar substance. Alcohol is a polar substance. If you mix alcohol and water, do they combine to form a solution together or a mixture? They bond together, right? Okay? They're attracted to each other. Here's something really creepy. If you take 500 milliliters of water and 500 milliliters of alcohol and you mix them together, what do you get? What do you get? 500 and 500? That'd be really creepy. You would think you get 1,000. You actually get 900 and some. You get less because when they bond together, they form a more dense structure. So, what? Any alcohol, doesn't matter. I don't care what you do. Do anything. They're all polars, same as water. Okay? So we're going to be doing a water lab with alcohol and water. We'll talk about that later. But you need to understand this concept in its conceptual form. All right. I think we did this. Okay, we're going to move on. I'll go back. Non-polar substances like oil, grease, and wax do not dissolve well in water. I just talked about that. Because those are covalently bonded substances. All right. So looking at ionic compounds in water, I just did that with you. So I don't need to go over this too much more, but just to give you an idea, remember, we have our sodium, that's positive, attracted to the negative end of water, and then over here, you have your, I got to look for it, chlorine, which is negative, attracted to the positive end of water here. It's a really fat pen. I got to make it skinnier. There we go. Yeah. So positive to negative, and over here I have positive to the negative oxygen. Okay? Yep. So if you look at that, it makes sense. Water's polar. It will dissolve things with charges because it has a charge on each end of it. So looking at hydrogen bonds. Oh, now we're talking about something a little different, close, similar. Now when bonded to an oxygen, nitrogen, or fluorine atom, a hydrogen bond has a partial charge nearly as great as a proton's charge. It attracts the negative pole of other nearby molecules, and this is what is called a hydrogen bond. It is stronger than the attraction between other molecules, but not as strong as a covalent bond. So it is strong, and it's stronger than an ionic bond, usually, but it's not stronger than a covalent bond. I'll give you a little example of that. If I jump into the water, the water won't catch me, will it? No. The bonds that hold water together are hydrogen bonds. So when I dive into the water, I go through it. If the bonds in the water were stronger than the bonds that hold me together, covalent bonds, I would hit that like a brick wall. It hurt, right? Okay. So hydrogen bonds play an important role in many of the molecules that make up living things. That's kind of a fun example to think about. But now what I want you to do is I want you to draw water, one water molecule bonding to another. I want you to draw one water molecule bonding to the other as best you can. As best you can. And if I don't answer the phone when I'm in the middle of learning with you, it's because what we're talking about is more important than that phone call at that very moment. I know when it's a counselor or something, that can usually wait, and they will call back if it's important. I found that out. So I will answer if they keep calling back, but if I ignore it once, it's because we're learning something important. Okay? What we're doing here is way more important than, they got gym class or something they can pull you out of. I want you right here, right now. That's okay. Log back in. Yeah, if you get bounced out of Pear Deck or something, just log back in. If you can't get back in, let me know, but you should be able to get back in. Get you started off to the right path. I'll give you a hint. You're going to start off with the molecule kind of like this. And you're probably going to want to mention that they have something going on like that, right? Remember? Oxygen, electron hog. So I know I joke around about oxygen being an electron hog, but that's like one of the underlining things in chemistry, especially in biochemistry. Because it is more electronegative, meaning it has more of the electrons, it always has that negative charge. DNA is charged negatively because of oxygen. We'll talk about that later. You guys are going to extract your DNA later on in the year. That's kind of fun. Nah, take a little sample. Tissue sample. See what we have here. So now I know there's 23, and that's what I should expect for responses, right? It's funny, the draw tool you guys like a lot. Okay, I've got... Okay, we're getting close, close. What's wrong with this one right here? Oxygen and oxygen are together. Does that make sense? No, because they're both negative. That wouldn't happen. Okay, I like that one's close. Close. No, 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 no. Good. Nope. Anytime you got oxygen with oxygen, it's no good. Close. Something like maybe that. I don't know. I got to see something. No, not quite. Okay, we're getting there. Getting there. All right. Well, let me give you my version. So I talked about this water molecule, right? And this water molecule, let's get rid of our pig drawing here for a minute. The water molecule is going to be attracted to another water molecule through this thing called cohesion. Water being attracted to other things is adhesion. Water attracted to itself is called cohesion. Okay? So if I were to draw another water molecule here, then I would want to show the attraction of the positive end of water to the negative end of water in a dotted line. That is what is called a hydrogen bond. It is called a hydrogen bond because it is unique to hydrogen, because hydrogen never gives up its electron, and it always has this polarity when it covalently bonds. That's why the attraction of one polar molecule to another is called a hydrogen bond. Is that pretty straight and forward? Yeah. I mean, when you look at hydrogen, you understand. It's like if you only had $1, you're not going to give it up, right? So you're going to hold on to that thing no matter what. H-bonds. Very important in biology. They're the bonds that hold DNA together in the middle. We'll talk about that later, how we can break them. But for right now, you need to understand that this dotted line, if you see a dotted line, that's a hydrogen bond. So let's talk about a few things. This right here, water to water, is what is called cohesion. You should probably be writing this down somewhere. Water to itself, cohesion. Are we a cohesive classroom? We're all working together on the same tool, using yeah, cohesive, right? We're bonded together. What's that stuff on the back of a sticker called? It's an adhesive. You stick it on something else, right? So that's where the word adhesion comes from. Let me show you an example of that. So I'm going to come over here to this window, and we're going to take a look at, oh, look, I don't even have to, like, do anything. It's a perfect day for it. What do you see on the window? Water. What is water doing to that window? It's sticking to it, right? What do we call it when water sticks to something? Adhesion. You add to it. Adhesive, right? Adhesion. So this happened to all of us within the last, hopefully, 24 hours. We all took a shower. And you got out of the shower, and the water didn't just hit the floor, did it? No. The water sticks to you. Why does it stick to you? You've got salts on you. Ah. What are salts? Ionic compounds, right? And water's attracted to it. And then the salt's bonded to part of you, and it's going to hold on to other parts of you too. What's the window made of? What is glass? Sand. What is sand on the periodic table? We're getting there. No, it's Si. What is it? Silicon, which is in what family? It's going to make a lot of sense in a minute. What family? Number 4. What does family 4? What is one of the very unique things about family 4? Who's above family 4? I meant, who's above silicon in family 4? Let me restate that. Carbon. The one that likes to bond with everything?
Oh boy.
So now, hey, folks, stay focused. So you're saying everything in family 4 likes to bond to a lot of stuff. It can be plus or minus 4, and then I throw a charged polar molecule at it, it's going to stick to it, right? Think about it. Plus or minus 4. Okay? It's got a lot of flex as to which end of water it bonds to. No wonder that drop sits right there and doesn't move. Right? Think about it. Water is more apt to fall off me than it is that window. Okay? Because of the properties of water to that window. Now I want you to think about this even more. We are made of both polar and nonpolar stuff. Proteins can be polar or nonpolar. So little secret things I'm not going to tell you about, but there's a lot of information you don't need to know that I'm going to kind of reference here. Anybody ever been water skiing or like tubing or anything, or been drugged behind a boat? Okay? So when you hold on to the rope and then the boat keeps going and you hold on, Brooke, what happens? Come on now. What happens? When you hold on, what happens? What's the water doing to you? Say it is adhering to me, Mr. Mason. It's adhering to you. Okay? Literally, water is grabbing you. It's bonding to you. And then you're like getting drugged through it, and all these water molecules are just clinging to you, right? And they're dragging you. It's called drag, right? That's what it's called. Okay, so anytime matter's attracted, that you get drag in planes and everything, right? So you get drug along and it's like ripping the skin off you. That's literally what it's bonding to your skin and then getting pulled off, right? Okay, so you put on what to decrease friction when you go in the water? Like a wetsuit, right? Okay, so if you put a wetsuit on, what is a wetsuit made of? Let's talk about it. Not silicon really, it's like latex, right? Do you suppose latex is polar or nonpolar? Nonpolar, non-charged. Why? Because if it was charged, it would bond to the water, and then you'd have a problem again. You might as well just have your skin on at that point, okay? Let me give you a little example of this. If I were to take Vaseline before I swam in a swim meet and rubbed it all over, and then jumped in the water, would I go faster? You bet you. It's illegal. You can't do that, but yeah. But it is completely illegal to do that for a reason, okay? You would go a lot faster. Plus, it'd be kind of weird, you couldn't get out of the pool. You might drown. They grab stuff and slip off. So there's that. Why do swimmers wear swim caps? Imagine all of the surface area in a million hairs or whatever you got up there, okay? And that water's pulling on each one, and it's like pulling your hair, right, the whole time. What do the boys do? They shave their legs, right, because they want to decrease drag. You could be faster if you did, okay? And so I think we understand that conceptually, but really what is happening is water is adhering to you. Okay, it's called adhesion. It's a very strong force. We don't even realize, but it's there all the time. Folks, let me talk about one more thing. We've got these long tubes that come back to our heart. They're called veins, right? The only way, and I mean the only way they get back is through this bonding. Okay? You think, gentlemen, if you think your heart has enough energy and pumping pressure to put blood back up to the lungs, it does not. There's too much gravity from the bottom of your toes to the bottom of your lungs, okay, and your heart. So you need capillary action. You need water bonding to itself and to the walls to climb up, literally, that tube. If you get a small enough tube, water will run right up it, right? It's like siphoning action. It's called capillarity. That's exactly how the water gets from the bottom of the roots up to the top of the leaves. You ever wonder about how it happens? Because plants drink through the ground, right? That water climbs all the way up using cohesion and adhesion together. All right? Now I'm going to need a volunteer. I'm going to stop this video because they won't be able to see it in the video. Oh, wait, no, I don't. Not yet. We have to finish notes. I'm almost done. Sorry, guys. We'll keep going a little bit longer. So, no, you can go back in the deal later. Here we go. So if I take a look at water and understand that water is charged, not overall though, right? Water does not create ions because hydrogen cannot lose its only ion. Because of that, you get this electronegativity in oxygen and this positivity in hydrogen, and therefore water will be attracted to itself. We call this what? This is the H bond, right? What else do we call it? That is cohesion, right? Okay? That's water to itself. What if water was attracted to, let's say, the window? What would we call that? That's adhesion, right? Okay, you should know that. So we've been talking about this. This is a big section. It contains a lot of things. We have to do covalent, ionic, and polar covalent bonding. We still have to do a water lab, which we will start on Monday. Give us something fun to do on a Monday. But all matter is made up of atoms. And remember, an atom has a positively charged nucleus surrounded by a negatively charged electron cloud. Don't forget it's that outside valence shell that we do all the bonding with. And the chemical bonds formed between groups of atoms because most atoms become stable when they have 8 electrons in the valence shell. Except for helium and hydrogen, they want 2. Inside holds 2. And remember the different types of bonds. Covalent is sharing, ionic is giving or taking, and you should be able to do both. The polar covalent bonds that we talked about today, that unequal sharing of electrons, the polar attractions and hydrogen bonds are forces that play an important role in many of the molecules that make up living things. And understanding what that does for us is huge in biology. Okay? Huge.